Swayam Prabha. Digital India. Educated India.
In the last class, we talked about the introduction to this course. In this class, we will be talking about the principles of maintenance. The question is, what are the techniques of maintenance available to us, and what kind of techniques and tools need to be known before we can apply maintenance to different plants, and which kind of maintenance is beneficial, where and how, and so on. Question is, why do we need to have a planned maintenance? Obviously, we always would not like to overdo on maintenance, because maintenance also involves cost. Okay, I would not like to re-maintain and maintain and so on, because it's for the sake of maintenance. Machine may be up and running and doing good, but then I unnecessarily do a maintenance. Okay, but sometimes, as you all know, for strategic reasons, sometimes we have to maintain it even if the things may be okay, and I would not like my trigger to jam in front of an enemy. Okay, I would not like my missile not to fire when I want it to fire. Okay, these are cases which we cannot take for granted, but of course which we do always. The OEM manufacturer of your car would have told, every 5,000 kilometer go to the service station to get your oil changed. Sometimes we do it, sometimes we do not do it, nothing goes wrong with it. Okay, sometimes we would have gone after 15,000 kilometer, only thing that the service manager there would tell you, sir, you should have come earlier and blah blah blah, but still nothing goes wrong with the machine. Okay, so the idea behind maintenance is that we would not like to do a lot of maintenance. We like to do a maintenance only when it is necessary, because if a perfectly maintained machine is available, it will do its function it was designed for. Okay, I would not like to have any loss of production caused by failures, right? Suppose imagine if my machine was never maintained throughout the year, and I have a deadline of March 31st, where I have to meet the annual production targets, and suddenly in the month of March my machine goes down and I require serious maintenance. You can imagine this is going to affect my balance sheet, but because for this financial year ending March 31st, I could not reach my achieved target because my machine had to undergo a maintenance. So these are plans, these are things which we should never do, because everything leads to loss of finance, and why am I doing maintenance? I need to have high revenues, high productivity at low cost. Okay, I would not like to lose orders when the market demand is high because my machines cannot produce. Okay, a planned maintenance, or a plant engineer or plant manager would have planned for its machines maintenance during a lean market time. For example, you can imagine Diwali firecracker manufacturer cannot have his machines down months before Diwali. Okay, it's going to hit the market, it's going to affect the market. So people always do plan. I'll just tell you an example of this. Auto companies, particularly auto companies in our country, sometimes in the month of July they do a planned maintenance schedule. Okay, and not towards the end of December, or not towards the end of, obviously not towards the end of the financial year. So everybody, knowing on the strategy of the requirement of their products, they find out a time when they will do a shutdown planned maintenance, but that does not mean that you will not do your day-to-day maintenance, you will not do your weekly maintenance, or so on. Okay, sometimes it so happens, if I know that only in the month of July I am going to overhaul my machine, I did not store my spares throughout the year. I did not store it from August to the subsequent July. unnecessarily, because I know from August to the next July I will be not requiring the spares, okay, because storing spares is inventory cost. I have to store them, I have to keep them, I have to keep a stock, do a bookkeeping on them. Maybe if I require the spares in the month of July, I may at most have them by the month of June. So my inventories reduces. Okay. These are, I mean, this may sound very trivial, but if you think of a large plant, sometimes the inventory is as high as the certain critical spares, but at the same time does not mean, if you are going on the high seas and you have a bearing for your propeller and you do not have a spare bearing, you will be in deep trouble. Okay. So depending on the situation you are in, you are the best judge what kind of critical spares to carry, what kind of spares not to carry, what kind of spares when to carry, and so on. Okay. And then of course, once we have maintenance properly, if I have a good maintenance schedule in my plant, I will always have a process which is very efficient, which will be producing quality as to having the best surface finish. For example, if I am a machine shop where I produced fine machined surfaces, suppose I have taken no care on the tool wear conditions, I may be having the workpiece surface very rough. I would not like to have a rough machined surface, because my say turning machine cannot run at high speeds, so I cannot have a smooth finish. Okay. There has been intermittent speed fluctuations in my machine, so these marks are going to stay up in your machining process. So even a simple lathe machine has to be taken care of, otherwise if you are doing a machining operation on that lathe, its quality is going to, the machine's quality is going to reflect on the workpiece. Okay. We take it for granted that you have a nice machine, somebody say this machine has a bad gearbox. Somebody may say, well, what has gearbox got to do with your tool? You have a new tool, so you should be having nice machine surfaces. But people do not understand that if you have a bad gearbox, there will be backlash and there will be a speed fluctuation, and that is going to affect the cutting process. They are all interrelated. As engineers, I am sure you will appreciate it much better that all these dynamics of the machine are interrelated, and they will eventually reflect in the final product which you are producing from your plant. Okay. And of course, I would like to have the plant once up, run till its maximum useful life. And of course, if all my machines are running at their best OEM specs, I will have the production capacity increased. Okay. I have seen many plants, they never run to full capacity because their machines, they would not like to overload them. They are not sure about the design capacity of the machine. They would have bought a new machine, it says it can be loaded up to maybe 100 horsepower, but they will not load the machine till 80 horsepower. Okay. They would say, oh, I would not like to reach the high levels because it may damage my machine. So these are uncertainties. Okay. They will say that the machine has not been maintained, so I would not like to load the machine and create excessive wear and tear to the machine. Okay. So again, if this maintenance is planned, like I was saying, the planned downtime, planned inventory, it is going to reduce the maintenance cost. Reduction in maintenance cost means increasing the overall profit, and the guys in the finance will always be happy if the cost for manufacturing a component comes down, because that brings about the overall production increase and revenue to the company, and that is what everybody strives for. I mean, why are we doing maintenance? Because I would like to have high productivity at low production cost or low maintenance cost. So this is a very familiar machine availability curve, and sometimes this is known as the bathtub curve. If you look at this curve, there are two axes here. One is the x axis is the time, and then you have the failure rate. There are 3 zones given by this blue, green and the wear out zone. When a machine is initially commissioned, the failure rates are pretty high. Okay. This could be because of wrong OEM specs, wrong integration, installation defects, not being able to understand the machine, not able to understand the performance of the machine, operators are not properly trained. So, these are issues by which we have always, you all must have faced. Maybe a nice example I always give to all my classes is, once you have bought a new computer or a laptop, okay. I mean laptops are pretty robust and pretty user friendly nowadays. I am talking about 10 years ago when people used to buy PCs. First few weeks they used to be tinkle with the operating system. This audio driver is not working, that hard disk is not being properly read. I am sure all of you would have experienced this. Okay. But once you are comfortable with your laptop, with the operating system, with the kind of softwares, it undergoes a smooth life. Okay. And this initial defects or downtimes, be it your laptop, be it your equipment, is what is known as the infant mortality zone. The reasons could be many: not trained staff, not trained engineers for installation specifications and the requirements not matching, and so on. And then once these teething trouble are taken care of in an equipment, foundation problems could be another. Excuse me, foundation problems could be another. We have this green period, and which is known as the useful period, this machine. And again, despite our best maintenance efforts, at some point in the time you will see that the failures happening quite often in the machine, and a point will come you will find that it is more expensive to maintain a machine than to buy a new machine. Okay. Or the cost, because of this frequent shutdowns or breakdowns in the machine, is not wise, not financially beneficial for you, and that is where we call a shot and then we discard the machine. Okay. So, the machine's availability is given by this function. Uptime is the time given for the useful period, and the denominator uptime plus downtime is nothing but the total time of the machine. Okay. So, we as maintenance engineers have to strive for having high uptime, high availability of the machine. Okay. There are 3 very important types of machine maintenance, and one is the very first one is the preventive maintenance, or what is known as the periodic maintenance, and followed by the predictive maintenance or the condition based maintenance, and the last one is actually no maintenance, which is known as breakdown maintenance or the reactive maintenance. And in this course we are actually going to focus on the second one, that is the condition based maintenance. In fact, I had told you in the first class that we are gearing towards all this instrumentation, signal acquisition, data acquisition, analysis, all because of this CBM. I need to know the machine's condition by monitoring its vibration, by monitoring its temperature, by monitoring its pressure, etc. So, we need by the flow conditions. So, we will be focusing on condition based maintenance in this course, but I thought I should tell you about what this preventive maintenance or periodic maintenance is. Periodic maintenance means that I will regularly follow a schedule of maintenance. There will be a time interval fixed, no matter if the machine is bad or good, I do not care. I will just go on and religiously maintain, replace the spares, and then my machine will be always up and running. Particularly in the defense, they do this kind of periodic maintenance because they have to be, because of strategic reasons, but that does not mean that they do not do condition based maintenance. Condition based maintenance is the technique wherein we always, I underline the word, we always know the condition of our machine, because certain extra capital investment has been done on the machine by instrumenting it with additional instrumentation in terms of transducers and sensors, and then we have an analysis unit, so that every time the machine is running I know its present condition. I also have its past history in my database. So, by certain algorithms I can say whether my machine is going to behave the present way or its condition is going to be okay or it is going to be worse. I can find out from the database of my data stored in my database from the previous conditions of the machine. So, predictive maintenance or condition based maintenance always depends on the present condition, sometimes on the past condition of the machine, but the machine's condition need to be known to do maintenance. Another thing I will tell you, in fact I was telling you earlier in our meeting, that like a doctor is no good to a dead man or a dead person, similarly a maintenance engineer cannot maintain a machine which is already dead, which is not running. Okay, I can at most repair it, but I cannot maintain it. Okay, a machine has to be running, so that once it runs, it is going to give us the signals. If a machine is not running, there will be no vibration, there will be no noise, there will be no heat generation. So, I cannot possibly do CBM on that machine. At most I may look into the manuals, look into the design and do a repair of it, but to implement CBM a machine has to run. Okay, so that it gives the required signals and I have the instrumentation to capture those required signals. So, I am stressing on the word signals instrumentation in the case of condition based maintenance, because of the fact that to implement condition based maintenance I need to have extra investment done on the, even a machine could be as new as I have just bought a new machine today. To implement CBM on it, I have to do an extra investment right today itself from day one. So, that I have the investment to take care of the instrumentation, investment to take care of the analysis unit, I have skilled manpower to analyze the signals acquired from the machine. Okay. As opposed to the last one, the breakdown maintenance or the reactive maintenance, this is actually no maintenance. I do not do any maintenance on this machine. I can afford to lose the machine if the machine goes down. Like I was telling you, in the case of a steel plant, I mean I have a blast furnace, I cannot afford to lose the blast furnace, but of course I can afford to lose couple of water coolers in my canteen. Okay. So, I mean if the water cooler in a canteen in the steel plant goes out, okay, I can always buy a new water cooler. Okay. And imagine the criticality of that equipment, but of course if my blast furnace is damaged and down, I cannot afford to lose that. Okay. So, these are issues which we will understand in the lecture on FEMICA, that is failure modes effect and criticality analysis. From the failure modes which will affect or function, I can know what kind of maintenance effort has to be put in which machine. Okay. So, I will be focusing this class or on predictive maintenance, because in predictive maintenance you will see in an example which I will show you subsequently, that the maintenance cost will come down with time, because of the fact every instance I know the machine's condition. Okay. I can always know whether my machine is going to undergo a failure, is going to have an abnormal behavior or not, and so on. So, because of that I will have few machine failures, I will have less repair downtime, because of the fact that I know the machine's present condition. I can always, for example, I will with time say I have a parameter which tells the machine's condition. For example, with time, this could be in intervals of 1 month, 2 month, 3 months, etc. So, this is in time in months. I have measured. So, here this is the parameter second month, and slowly I see this is happening. Okay. So, if I was trying to do a trending of the machine's condition towards the 4th to 5th month, at the end of the 5th month, as a maintenance engineer, I would be getting worried. Well, now something is behaving abnormal with this machine, and why is this parameter coming down? So I know, well, by 6th or 7th month, I need to have a major repair or study into the problem in this machine, so that I may be having certain critical spares already available to me by the 6th or the 7th month. So that from the month 1 I did not store this critical spares. If I know it takes only 1 month to get this critical spares, I can plan by the end of 5th month to get this critical spares. That is one way of looking at it. Okay. And then I can be prepared that my machine is going to have a downtime, so I can for example, I will give you an example here. Suppose we have a festival of Dashera, wherein we give holidays to our workers. Okay. Imagine at the peak of Dashera, my machine which is to be producing, and there is a demand that it has to take a serious breakdown. So I have to pull out my workers or engineers from their Dashera vacations or holidays. I have to pay the workers overtime because I have to pull them out from a scheduled holiday. I have to have the spares ready. So these all add to cost. But had I planned it earlier, and because I know the machine's condition, well, at the end of 4th month, I know I'll have a high production demand toward the end of 7th month. This is the time wherein I can take a repair. Okay. So these are the cases wherein I can do the reduce my inventory, and then of course if I do a proper downtime, I can reduce the machine's availability and increase production. And if I know this machine is going to have an abnormal behavior, I would not like my operator to be very close to the machine. Okay. I have had a case wherein we have a plant in very close to Kharagpur, Haldia, of a large FMCG manufacturer. One night the plant engineer gets a phone call that the gearbox in fact blew apart. Okay. And this is a plant which they produce detergent. Okay. Detergent production is very similar to cement manufacturing. They have a mixing, they have a rotary kiln, and that rotates at a very low RPM, and then it's heated at one end. So if you have a motor running at 1500 RPM and this kiln is rotating at 2 to 3 RPM, you can imagine the amount of reduction being brought about in this gearbox. And this gearbox was very critical to that detergent plant. And this gearbox, because of reasons we will find out later on, in fact that's a case study I will discuss towards the end of this course, that this gearbox blew up. Okay. Imagine if the operator was standing next to it. Unfortunately it was in the late night shift and nobody was there. Okay. Imagine if an operator was standing next to it, it would have been dangerous. So if we know the machine's condition, we know when it is safe to go closer to the machine while it's operating and so on. Okay. So all these are the benefits of predictive maintenance, and in this course, as I was telling, we will be focusing more towards the condition based maintenance. Now I always give this example to all my classes on the economic analysis as to I am doing a comparison on the predictive maintenance and the preventive maintenance. The question is which one is good and which one is not good in the long run. These are few budget heads. First one, I don't know if you can see this, is the capital maintenance equipment cost. Day one I would require an addition, though both my machines are new, I am just doing a comparison, both my machines are new. Day one I would require an additional expenditure towards the signal acquisition, the transducer, the analysis unit. I need to have that in place. But for a preventive maintenance or a periodic maintenance, I require no investment. Okay. Now let us look at the case of the preventive maintenance, assuming there are 4 shutdowns a year. By for shutdowns I mean 4 scheduled maintenance in a year, and the total cost of this maintenance, which includes the machine downtime, the repair, labor cost per shutdown for repair, is 50,000 rupees. for 4 such repairs in the preventive maintenance cost, at the end of first year I would have spent 2 lakh of rupees, right. At the end of 10 years, if I was religiously doing this preventive maintenance, I would have spent 20 lakhs. At the end of 20 years, I would have spent 40 lakhs. Okay. And then if you look at the, because I am doing predictive maintenance, I am not doing maintenance on a regular schedule. I am only doing a maintenance as and when the signal indicators let me know that this machine requires a maintenance. And usually this is a figure that at the end of 20 years, if there are only 5 shutdowns because of maintenance, since we are doing predictive maintenance, the number of shutdowns will be less, and this happens to be 5. And this is not a data which I have cooked up. Okay, this is the data which is there from the survey report given by industries in many journals, and this is a compilation of such. In the span of 20 years, there are only 5 shutdowns. So 5 lakh is my initial investment, and then I would have spent an additional 2.5 lakhs. So the end of 20 years, I would have spent only 7.5 lakhs if I was doing predictive maintenance, whereas I would have spent 40 lakhs in the case of preventive maintenance. We do not realize that, but this is the statistics obtained from industry who are doing these as benchmark studies and have reported them in journals. But always we have a problem with the engineers, maintenance engineers, asking the management for more investment right day one, because the management would obviously say, well, we have just bought a new machine, why do you require an additional expenditure of 5 lakhs for maintenance? Because from day one I need to do a predictive maintenance so that I have the right equipment and infrastructure to acquire the signal and know the machine's condition. So that is why this 5 lakh has to be spent there in the day one. But in the long run, we spend we save about more than more than about 32 lakhs in 20 years if you do such an accounting. And in fact, nowadays, I'm telling you the scenario of the Indian industry. In fact, there are many plants. I'll just give you the examples in the last 2 decades. Okay, about 2 decades ago, okay, people hardly knew about vibrations. Okay, vibration was always there. Even in engineering curriculum, we are hardly being taught machinery vibration as a full-fledged course. Okay, and in the industry, they used to have some meters, used to just give you just one number, and there are certain ISO standards as to certain horsepower. This has to be the overall vibration level, and there used to be just a few people in a maintenance cell, workers and technicians. They used to go to the machine, measure its vibration, and forget about it. Okay, if there was a breakdown, people would blame each other. You have not recorded the vibration. They used to go back to their old log books, log books torn, pages flying here and there. And this was actually the scenario 20 years ago. When people used to call me to the industries to fix their problems, I used to ask them, do you have any vibration data? They would show me old log books, written sometimes by pen, sometimes by pencil, sometimes they do not know by in what units they have recorded the data. Sometimes they do not know. I have seen they have not put the transducer in the wrong place. They do not know if there was a proper battery in the meter. They see some display, they write it down. There was no calibration of the meters, and this was actually the scenario 20 years ago in our Indian industry. Okay, but today the scenario is altogether different. Okay, if you go to any industry, they have smart screens everywhere with touch screens next to the machine. They have instrumentation transducers mounted on the machine. Data will be automatically logged into the data logger. Engineer just goes, touches the touch screen, sees the data logs, sees the trending chart, and there are subroutines, algorithms which will tell you when the machine is going to have a downtime, and this is the state of the art in the industry nowadays. Okay. And now you will see wireless coming a big way into the industry. There are no more long cables lying here and there. As I was telling you, monitoring machine sitting in Kharagpur, monitoring machine in Alaska is not a science fiction anymore. Okay, it is possible because of the advantages and the advancements done in electronic instrumentation, in computers, in miniaturization of the transducers. Transducers are smart enough, they are fault tolerant, they can be self calibrated by techniques. Okay, because these are the advantages of predictive maintenance, and engineers are smart as you are nowadays. Okay, everybody understands instrumentation, everybody understands computers and electronics, everybody understands computer languages, everybody understands vibration. Okay. So, there has been a paradigm shift in maintenance engineering in the industry, both in the academia and in the industry. Okay. In fact, nowadays the we are talking about predictive maintenance. Nowadays the focus has been to, if there is a problem in the machine, they would like to know what is creating the fault in the machine, and next is there are mathematical algorithms as to find out the remaining useful life of a machine, and that is very important. I mean, obviously to an engineer, the very next question is, well, my machine is running fine, when is it going to go down? Now, that is the question everybody asks. Your management would ask you, I mean, can my machine survive for next 10 years? Okay. And how would you answer that? You have no clue. All you know is you have data till present from the past 10 years. You cannot. So there are a lot of mathematical tools available, models available, which will let you know whether my machine is going to survive for the next 10 years or next 15 years, or when it is going to have a condition wherein the machine will be totally unacceptable. Okay. So you all can understand the benefits of predictive maintenance by the small example which I showed you. Now, what are the techniques available for predictive maintenance? As I was telling you, you had some idea about the techniques available for predictive maintenance. In the last class I told you about that 70% of the cases of predictive maintenance is by vibration monitoring, followed by wear, debris and the oil analysis, which is the remaining 20%, and then next comes the motor current signature analysis, the thermography and the NDT techniques, which is the remaining 10%. I will just to give you an example on thermography. I will just tell you an example which the industry nowadays is using to save power lost during power transmission. You know, this high voltage transmission towers, okay, wherein they have a certain switch gears. They will be operating a switch gear, and suppose from one transmission tower line goes to another grid, they will be having switch gears, okay, and this switch gears have to make contact, okay, and this is high from the ground, and then you are standing somewhere here. Obviously this is 25 kV or 33 kV lines or 132 kV lines, okay, and they are transmitting electrical power. Okay. Now imagine in this switch gear, if there was a excuse me, loose contact, okay, there will be, because of loose contact, there will be arcing and there will be heat generation, and there will be loss in power transmission. In fact, this is a case study reported by Andhra Pradesh State Electricity Board. I was there in one of their FICCI meetings, and they were mentioning that they have done a substantial amount of power savings in the power distribution by ensuring that there is no loose contact in the switch gears while at such high voltages. And how did they find out that switch gear loose contact? Obviously, because if it is a high voltage power generation, I cannot physically climb up the tower and check with a measurement. What they did was they had Jeep mounted thermal imaging camera to shoot at the switch gear and find out the hot spots. Okay, and they did a lot of, because the electricity board reports to the FICCI that there is a lot of power loss in the transmission itself, not in the generation, but in the transmission, and switch gear, loose switch gears was a very, very large component, and that they could reduce by doing thermography. Okay. Thermography we use in detecting faults. We may not be able to diagnose, for example, a coupling between a pump and a motor. If there is a misalignment, I can put a vibration transducer, measure the vibration, do an analysis and tell, well, there is a misalignment. But offhand, just to know whether there is a coupling misalignment, I will just shoot the camera on the coupling. If the coupling is hot, I know something is wrong. So, I can identify hot couplings, I can identify hot bearings in the case of the railway axle, I can identify hot conductors behind a panel. For example, you are talking about a ship which comes to the port for few days for an overhauling. I obviously cannot remove all the claddings and the panels and to see all the conductors whether anything is hot. You can just do a thermal imaging scanning and find out the hot conductors and then take corrective measures. Okay. So, thermography is a very, very quick and easy way to detect abnormal heat changes, and this abnormal heat changes could be because of misalignment, could be because of loose contact, could be because of high current being flowing in the conductor, etc. Okay. And this NDT technique is another technique wherein we have the techniques of ultrasonics, the techniques of acoustic emission, borography. How do you detect crack in a shaft from the outside? For example, you would have done a fine casting of a cylinder block. Okay, the engine, they do a casting of the cylinder block, and some of the surfaces are machined and components are fit into that machined cylinder block. But if there is a thin hairline crack in that casting, and because everything will be under high pressure, during the operation of the engine, the oil or the flue gas or the combustion gas, etc., are going to leak out. Okay. And then you will lose compression in the engine, and this engine is going to be no good. So, how do you detect such hairline crack on a surface? A surface you possibly cannot see through your naked eyes, everything will be nice machined, but there will be thin cracks. So, this is what is known as the dye penetrant test. You can put a layer of dye, and then under a special camera you can see this dye will glow, and you can know whether the crack is visible, crack is present or not. So, certain NDT techniques are used for finding out defects in the machine. Ultrasonic is very popular in the sense, I will just give an example of ultrasonics. Say for example, I have a metal piece and there is a crack here or void. So, if I have an ultrasonic transducer, this ultrasonic transducer, what happens is it gives a wave, okay, incident wave, and this is a denser material. This is of another material. So, there is a density difference at this interface. So, because of this density difference, there will be a reflected wave. So, in this transceiver, you will see a pulse, and if you rove this transducer, every instance you will see a pulse, intensity equally spaced. But when the scenario, when it comes here, just right above the pocket or the void, because of the density difference, this is going to bounce back. So, you will see suddenly a very close spacing, and then again, okay, this is say time, some voltage level. So, this means, because the time taken will be less, because the distance travelled is less. Okay. So, this means that there it came across an obstacle which was of a different density than this common homogeneous material. Okay. And that is the principle behind ultrasonics. Ultrasonic waves are, as you know, high frequency, they are very directional, because high frequency waves are directional, like you would have heard of a siren. If there is a siren at high frequency, you always turn your heads towards the siren, because high frequency sound or noise are directional. Same is true with ultrasonics. Okay. So, if I have an ultrasonic scanning of this, I can do that. In fact, the ultrasonic thickness gauge is based on this principle. Okay. If I know the speed of the ultrasonic wave in this medium, I can calculate the, from the time taken, I can calculate the distance or the thickness of the specimen. In fact, ultrasonics are used, another way is to find out the, in a lot of these tubes, a lot of the large tubes, of certain cross section, whenever they carry a lot of chemicals, either some things get deposited, clogged. Because of this clogging, what happens, the thickness as measured here, suppose originally this was a 10 mm thickness, because of with time, because of this deposition of the solid particles, there will be variation to this 10 mm. And if you rove an ultrasonic transducer all around the circumference of this tube, you will know whether in the internal, which is not visible, I mean possibly vibration monitoring cannot measure it, but if I can rove a transducer all around the circumference of this tube, I can know what is wrong in this, if there is any formation, any deposits in the inner wall of the tube. Okay. People of course use radiography also, X-rays is another way of doing it. So, there are many ways to do such NDT techniques like ultrasonics, acoustic emission, radiography, etc. Now, to implement all this CBM or condition based, these parameters, vibration, wear debris, oil, temperature, current, process parameters, these items written in green are actually the transducers required to sense these mechanical parameters. And these transducers could be, for vibration it is accelerometer, and for this wear debris it is the spectrophotometer, because as I was telling you, in this wear debris, the wear debris fall off a parent material. By knowing the wear debris chemical composition, I can know, comparing knowing the chemical composition of the parent material, I can very well know where this or which component has worn out, and because of which this particle has got deposited in the lubricating oil. So, that is done with a specialized equipment known as a spectrophotometer, and spectrophotometers are a very expensive equipment. They require specialized facilities to operate. So, obviously, I cannot be putting a spectrophotometer next to a gearbox in a cement plant. Okay. Spectrophotometers are in dedicated central research facilities. In IIT Kharagpur, we have several of them in many departments, wherein all we do is we bring in the oil sample. We can, through a spectrophotometer, we can know its chemical constituents. We can know the composition of this wear debris particles as to what percentage of iron is present, what percentage of zinc is present, copper is present, etc. And then of course always compare with the chemical composition of the parent material and see if zinc is in that component and I have a strong amount of zinc in the wear, I know that parent component has worn out. Oil, there are many ways to measure the parameters in the oil, but one very handy way is to known as the particle count meter, as to what is the size of particles available in the particle and what is their concentration in parts per million, how many such particles are there. Temperature, infrared detectors, RTDs, thermistors, etc. can be used to detect temperatures. Electrical current, you can use the simple ammeter, but Hall effect sensor is a technique which has a very high frequency response, because I was telling you in the motor current signature analysis, it is just not the amplitude of the current, but it is the nature of the current in terms of its frequency contained. It is just not 50 hertz, but it could be 50 hertz and also frequencies around the mechanical defect frequencies, which is being driven by this of the mechanical unit, which is being driven by this electrical motor. So, on Hall effect sensor is a transducer which is used to monitor electric current, and then next comes the process parameters as to the finding out the flow rates of the processes, particularly in chemical process plants, in fertilizer plants, etc. People would like to monitor the flow rate with an orifice or a venturi meter or a turbine flow meter. There are a lot of pressure gauges to measure the pressure in the chemical process and so on. So, these process parameters indirectly will give a clue as to what is wrong with the machines running that chemical process. Now, you have a fairly good working idea about the components in the predictive maintenance system. We of course need to have the machine, we need to have the transducers, we need to have the data acquisition unit, we need to have the computers where the data has to be stored in a database, we need to have a skilled manpower and an analyst who will analyze this data. And so, a very generic predictive maintenance system will have the user friendly hardware and software. Hardware could be the transducers for measuring vibration, transducers for measuring the pressure, process parameters, transducers for measuring the temperature, the transducers for measuring the current, etc. and on software which will tell when to acquire the data, how much of data to acquire, how long to acquire, and so on, what are the data to be acquired simultaneously. So, once this software drives this whole thing, this data has to be stored acquired by a computer aided data acquisition. It need not be just one data at a time, it could be multiple sensors at all times. I could collect data from all 16 sensors around my machines at one given instance, because there will be a lot of statistical processes, signal processes, wherein we will find a relationship between two signals, whether they are related or not. Otherwise, we cannot, if they are, if I do not acquire them at the same time, it is very difficult for me to tell them that they are related, because once they have to be correlated, they have to be acquired at the same time. And then we need to have a data management system which will be responsible for storing the data and doing the trending. Because if this has to be automated, imagine if my plant, if a steel plant have hundreds of gearboxes and pumps, obviously everybody cannot be running to each machine and doing a data logging or data taking by hand. So, this has to be automated, this has to be through a computer driven system. It may have cable, it may not have cable, it could be wireless, but all these databases with the proper nomenclature and identity of the machine has to be taken in. And then today I have a system for a steel plant, the same system perhaps could be used in a cement plant. The vibration transducer is the same, the principles are the same, only thing is that I have to mount, instead of a steel plant, I have to mount it in a cement plant. So, a system has to be very automated, it has to be flexible, and of course, it has to be reliable. I mean, garbage in is garbage out. If I give a junk data to my computer, it is going to give me a junk output. That should not happen. Okay. And then the reliability, it has to be accurate, the transducers have to be calibrated, and then it should not give any false trending and so on. Okay. So, while coming to a close, I would say the predictive maintenance management is a philosophy that uses the actual operating condition of a plant equipment and systems to optimize the total plant operation. Okay. It uses the actual plant operating condition, it cannot be of a dead plant, and then it is a condition driven preventive, it is a condition driven preventive maintenance program, wherein in predictive maintenance we assume that the machine will degrade, sometimes because of some slips unnecessary repair may be done, of course, but downtime can be controlled, whereas in reactive maintenance, because I have done no maintenance, suddenly I have to have high expenses involved, high spare parts, high overtime, because on a rush day I have to repair this machine, spares not available because machine has suddenly undertaken a breakdown, I have to import it. So, these are the disadvantages of the reactive maintenance. So, to have a successful maintenance program, I need to have these conditions there, dedicated manpower who understand the entire process, and there has to be good communication between the place where I am taking the data and where I am doing the analysis. I sample oil from one machine, and the technician on the other end is thinking it as machine B, where you took the data from machine A. Labeling and data communication between the labs is very, very essential. Okay. So, some of the plants, as you all know this by now, that these are the common elements in the plants and machineries which we will be talking about in this course, and this is the generic arrangement of CBM, the transducer, signal conditioner, and the signal analysis unit. Okay. And you will see CBM is almost used everywhere, and in the subsequent classes you will see how we use them to different machines. Okay. Thank you. Those of you who need to go